Hello again. As you know, this is the month of the Nobel Prizes, including the Nobel Prize in Physics for macroscopic quantum tunneling. So it seems an opportune time to talk about quantum tunneling. So what is tunneling? Well, the Schrodinger's equation admits of solutions where the wave function penetrates into classically forbidden regions where the total energy of the particle is lower than its potential energy in the region. Although the wave function decays exponentially under the barrier, the wave function exists also on the other side of a finite length barrier. Thus, there is a non-zero probability for the particle to pass through the barrier, although it does not have enough energy to do so classically. If we consider a double well potential with the particle confined initially to the left well, V0 is the potential energy barrier between the two wells. E0 is the 0-point energy of the particle and kT is its kinetic energy, both the vibrational and translational components. And the total energy available to the particle, which is E0 plus kT, is less than the potential energy needed to cross the barrier classically. Then the tunneling probability is proportional to e to the power minus 2 beta L, where L is the width of the barrier and beta is related to V0 minus E. We can see the same thing here in a multi-dimensional potential energy surface. E0 is the 0-point energy, V0 is the barrier, and kT is the kinetic energy, and the E0 plus kT is less than. The consequences of quantum mechanical tunneling have been known for quite some time. In 1928, George Gamow realized that tunneling is the reason behind the decay of some heavy atomic nuclei. Although the strong force confines the particle in the nucleus, creating a potential barrier around it, alpha particles can sometimes split off and escape the barrier, leaving behind a nucleus that has been transmuted into another element. So let us derive the tunneling probability in a simple case, tunneling from region 1 to region 3, separated by a barrier which is a flat barrier in region 2. So in region 1, where x is less than 0, the potential is 0. In region 2, where 0 less than or equal to x less than or equal to L, the potential is equal to V0. And in region 3, where x is greater than L, the potential is again 0. In region 1, the Hamiltonian for the particle is just the free particle Hamiltonian, and the Schrodinger equation is the free particle Schrodinger equation. In region 2, the Hamiltonian is the kinetic energy plus the potential energy of the barrier, giving rise to this Schrodinger equation. And in region 3, the Schrodinger equation is again that for a free particle. Now we apply the boundary conditions, that is that the wave function should be single valued and continuous across all three regions. So at x equal to 0, psi 1 has to be equal to psi 2, and at x equal to L, we again require that psi 2 has to be equal to psi 3. We also require that the momentum should be single valued. So from that we again get these two equations. In regions 1 and 3, the free particle solutions have the general form psi 1 equals a e to the power ikx plus b e to the power minus ikx, and psi 3 equals f e to the power ikx plus g e to the power minus ikx, where a, b, f and g are constants. And since the potential energy is 0, the total energy is equal to the kinetic energy, which is h cross squared k squared by 2m, from which we get k equals root 2 me by h cross. In region 1, we have two waves, the incident wave moving to the right, which is a e to the power I kx with intensity modulus of a squared, and the reflected wave moving to the left, which is b e to the power minus I kx. In region 3, we have only the transmitted wave moving to the right, so that g equal to 0 and psi transmitted is equal to f e to the power I kx with intensity modulus of f square. The tunneling probability is then the transmitted probability divided by the incident probability, which is modulus of f by a whole square. In region 2, that is under the barrier, the Schrodinger equation can be rewritten as d squared psi 2 by dx squared equals beta squared psi 2, where beta squared equals 2m by h cross squared into v0 minus e, which has to be positive because v0 is greater than e. Unlike in regions 1 and 3, the general solution in region 2 is not oscillatory, and instead we have psi 2 of x equals c e to the power minus beta x plus d e to the power beta x, where c and d are constants. Applying the boundary conditions to determine the constants from psi 1 at 0 equals psi 2 at 0 and psi 1 equals a e to the power I kx plus b e to the power minus I kx, and using this equation we get a plus b equals c plus d. From the condition psi 2 at L equals psi 3 at L and psi 3 equals f e to the power I kx, and again using this equation we get f e to the power I kl equals c e to the power minus beta L plus d e to the power beta L. Similarly, using d psi 1 by dx at x equal to 0 equals d psi 2 by dx at x equal to 0, and differentiating we get ik times a minus b equals beta times d minus c. Likewise, using d psi 2 by dx at x equal to L equals d psi 3 by dx at x equal to L, and differentiating we get ik f e to the power ikl equals beta times d e to the power beta L minus c e to the power minus beta L. After some algebra, it can be shown that f by a is equal to e to the power minus ikl divided by hyperbolic cosine of beta L plus I gamma by 2 hyperbolic sine of beta L, where gamma is equal to beta by k minus k by beta, and the hyperbolic cosine and sine are given by these formulae. The tunneling probability is then modulus of f squared by modulus of a squared, which is equal to 1 upon cos squared beta L plus quarter gamma squared sine squared beta L, which again after some algebra can be shown to be approximately equal to 16e by v0 times 1 minus e by v0 times e to the power minus 2 beta L. Recall that beta is equal to root 2 m v0 minus e by h cross. Thus, the tunneling probability decreases exponentially with the increasing width of the barrier L and with the difference in energy between the barrier and the particle v0 minus e. That brings us to the 1973 Nobel Prize for Physics, which was awarded to Leo Esaki and Ivar Giaever for their experimental discoveries regarding tunneling phenomena in semiconductors and in superconductors respectively, and to Brian Josephson for his theoretical predictions of properties in a supercurrent flowing through a tunnel barrier, in particular the phenomena generally referred to as the Josephson effects. In 1958, Leo Esaki at the Sony Corporation Research Laboratory in Japan showed the existence of tunneling phenomena in a semiconductor. And in 1960, Ivar Giaever at the General Electric Research Laboratory in Schenectady, New York, demonstrated the tunnel effect through a very thin layer of oxide surrounded on both sides by metal in a superconducting or normal state, thereby providing direct evidence for the existence of an energy gap in superconductors. This is an important prediction of the Bardeen-Cooper-Schrieffer or BCS theory of superconductivity. In the BCS theory, proposed by John Bardeen, Leon Cooper, and John Robert Schrieffer in 1957, superconductivity arises due to Bose condensation of Cooper pairs. A Cooper pair is a pair of electrons or other fermions bound together at low temperatures into a composite boson due to electron-phonon interactions, with the phonon being the collective motion of the positively charged lattice. The pairing interaction is quite weak, with an energy of approximately 10 to the power minus 3 electron volts, and it is long-ranged. Electrons in a Cooper pair may be hundreds of nanometers apart. So, thermal energy can easily break apart the pairs, and it is only at very low temperatures that a significant number of electrons are bound together into Cooper pairs. Since a Cooper pair has integer spin, either 0 or 1, its wave function is symmetric under particle interchange, and many Cooper pairs can thus occupy the same space, which is Bose condensation. This tendency for Cooper pairs to Bose condense together into the same ground quantum state gives rise to the phenomenon of superconductivity, where electrical resistance vanishes and magnetic field lines are expelled from the material. This is known as the Meissner effect. So here we see a superconducting material above the critical temperature for superconductivity, and below the critical temperature this material starts behaving as a superconductor and the magnetic field lines are expelled from the material. In conventional superconductors, the two electrons in a Cooper pair have equal and opposite momenta, so that the Cooper pair has zero center of mass momentum. At sufficiently low temperatures, electrons near the Fermi surface become unstable against the formation of Cooper pairs. Such binding occurs in the presence of an attractive potential, no matter how weak. In conventional superconductors, this attraction is attributed to electron-lattice interaction. The 1972 Nobel Prize in Physics was thus awarded to John Bardeen, Leon Neil Cooper, and John Robert Schrieffer for their BCS theory of superconductivity. John Bardeen, by the way, had already won the 1956 Nobel Prize in Physics for his discovery of the transistor. This image shows the discoverer of superconductivity, Heike Kamerlingh-Onnes, who won the Nobel Prize in Physics for 1913. And the others in this image are Paul Ehrenfest, Henrik Anton Lorentz, and Niels Bohr. So what is the Josephson effect? Two superconductors joined together with a thin insulating barrier between them is called a Josephson junction. In 1962, the English physicist Brian Josephson performed quantum mechanical calculations for such junctions and predicted that Cooper pairs can tunnel without resistance across an insulating barrier, giving rise to a zero voltage current across the tunnel barrier between the two superconductors. A constant voltage difference across the barrier results in a high frequency tunnel current in the microwave range. This Josephson effect was experimentally confirmed at Bell Labs in 1963. This tunneling electron current is exploited in the scanning tunneling microscope. In a scanning tunneling microscope, a surface at constant potential is scanned by moving a narrow tip along the surface. When the STM tip moves close to a surface atom, electrons can tunnel from the surface to the tip. This tunneling electron current is constantly monitored, giving information about the elevation of the tip above the surface at each location xy. So L is the width of the insulating gap across which the electrons have to tunnel, and that is related to the tunneling current, thus generating a detailed topographical map of the surface. This led to the award of the 1986 Nobel Prize in Physics to Ernst Ruska for his fundamental work in electron optics, and for the design of the first electron microscope, and to Gerd Binnig and Heinrich Rohrer for the design of the scanning tunneling microscope. Superfluidity is another consequence of Bose-Einstein condensation of a macroscopic number of bosons into a single state. At very low temperatures, helium-4 atoms, which are bosons, occupy a single macroscopic superfluid state. Helium-3 atoms are fermions, but they can also form Cooper pairs and condense into a superfluid phase at low temperatures. The 1996 Nobel Prize in Physics was awarded to David Lee, Douglas Osheroff, and Robert Richardson for their experimental discovery of this superfluid phase. Anthony Leggett won the 2003 Nobel Prize in Physics for his pioneering contributions to the theory of superconductors and superfluids, specifically for developing the theoretical understanding of superfluidity in liquid helium-3. It is important to be clear about superposition states and entangled states. If we prepare n particles, such that each particle is in a superposition of psi plus and psi minus states, and there is no entanglement between the particles, then the wave function is psi plus plus psi minus of particle 1 times psi plus plus psi minus of particle 2, etc. until times psi plus plus psi minus of particle n. And a measurement distinguishing between psi plus and psi minus on any single particle would collapse the superposition of the measured particle but leave the rest of the condensate unaffected. On the other hand, if all the particles are entangled such that the wave function is psi plus of 1 times psi plus of 2 times psi plus of 3, etc. until times psi plus of n, plus psi minus of 1 times psi minus of 2, etc. until times psi minus of n, then a measurement that distinguishes between psi plus and psi minus on any single particle will now collapse the superposition for all the particles. In 1978, Leggett suggested that macroscopic quantum tunneling between these two distinct components of an entangled state could be realized in superconducting circuits at millikelvin temperatures. This is because such superconducting circuits have very weak coupling to dissipative degrees of freedom in the environment due to their very low resistance. Anthony Leggett and his student Amir Caldera investigated how the tunneling rates would be affected by a weak residual coupling to a dissipative environment. Such macroscopic quantum tunneling can be realized in a current-biased Josephson junction shown here along with its circuit diagram. That brings us to this year's Nobel Prize in Physics, which was awarded to John Clark, Michael Devorey, and John Martinez for the discovery of macroscopic quantum tunneling and energy quantization in an electric circuit. In 1984-85, Clark, Devorey, and Martinez at the University of California, Berkeley demonstrated both quantum mechanical tunneling and quantized energy levels in an electrical circuit in a macroscopic system, a system large enough to be held in one's hand, a system with billions of Cooper pairs that filled the entire superconductor on the chip. In the circuit, the superconducting components were separated by a thin layer of non-conducting materials, that is, a Josephson junction. Collectively, the billions of Cooper pairs moving through the superconductor comprised a system that behaved as if they were a single particle that filled the entire circuit. This macroscopic particle-like system is initially in a state in which the current flows without any voltage. The system is trapped in this state as if behind a barrier that it cannot cross. The system shows its quantum character by managing to escape the zero voltage state through tunneling, which was detected through the appearance of a voltage. The macroscopic state has quantized energy levels which could be excited by microwave irradiation of different wavelengths. Here V equal to 0 is the zero voltage state. and this V0 indicates the height of the potential barrier. Irradiated with microwaves, the zero voltage state had shorter lifetimes when the system contained more energy. The tunneling probability, as we saw, is proportional to e to the power minus 2 beta L, where beta is related to the energy. In the actual experiment performed by Clark, his student Martinez, and postdoc Deveray, they changed the potential barrier. Okay. It involved irradiating a junction with 2 gigahertz microwaves and varying the bias current to change the potential barrier, thereby observing tunneling out of the first excited state, the second excited state, and the third excited state. This shows the so-called tilted washboard potential for the bias current less than a certain critical value I0, where the particle can be trapped in a metastable local minimum. For the bias current greater than I0, the particle accelerates, giving rise to a finite voltage V not equal to 0. Classically, the particle is trapped in the zero voltage state, whereas quantum mechanically it can tunnel through the barrier. This shows the results for the effective escape temperature that would give the measured escape rate versus the real temperature. The measured escape rates below the crossover temperature in the expected macroscopic quantum tunneling regime yielded results in quantitative agreement with theory. This is the theoretical prediction for the macroscopic quantum tunneling escape temperature, whereas these are the experimental results for a quantum junction, whereas a classical junction would yield these open circles. Okay. A superconducting circuit is one of the promising technologies being used to realize controllable quantum two-level systems, or qubits, as the basis for a large-scale quantum computer. We will stop here today, but we will talk more about quantum computers next month. See you later.